Okay, well, the problem was example 2, no? Que es C equal e to the x sin y. However, x and y depending of the another variable, que es s t squared and y is equal x squared t. Now you need to find, for example, the partial derivative is z with respect to s, because s and t are our independent variable, and partial z with respect to t. Remember the famous trick we are doing is z depending of the two intermediate variables x and y depending of the two independent variables s and t. S and t, S and t, S and t. The formulas, look in the diagram to compute, for example, partial z with respect to the s is partial z with respect to x, for example, time partial x with respect to s plus partial z with respect to y and partial y with respect to z. The z, no, the s. We ending in the same. Basically, the thing we are doing is moving to this patch. That one, that one, that one, and that one. Likewise, partial z with respect to t is partial z with respect to x, exactly the same as this. Now, partial x with respect to t plus partial z with respect to y times partial y with respect to t. Okay, this is our formula, and the rest is super easy because you differentiate one by one separately, and finally you integrate, put everything together. Okay, for example, partial c with respect to x is, you take that expression, no, the original expression, and differentiate with respect to x. By coincidence, it's the same. It's e to the x sine y, because the derivative of the exponential when the base is e is the same, and sine y is considered constant, no? Pero constant multiplier. Okay, now dz dy is, well, in that case, the variable you consider variable is y, and x is a constant. So e to the x is a constant, and derivative is sine cosine. Cool. Now, dx ds is, you take this function and differentiate with respect to s, que es t squared. The derivative s with respect to s is 1. Now, partial y with respect to s is this expression is 2st, no? 2st. That one with respect to x, s. Now partial x with respect to t is 2st or 2ts, doesn't matter the order, and partial y with respect to t is x squared. Now, final answer, I put everything together. So you replace in any expression, for example, d partial z with respect to s is equal. So now you copy that. You copy this guy is this, no? But normally the final answer is, you know, expressed using no the intermediate variable x and y. No. Using the last independent variable, which is s and t. So you replace. You put e. I copy this e, pero x is st squared, right? Sine what? Sine y, que es s squared t, multiplication by partial derivative x with respect to s, que es partial derivative x, es this, no? Partial derivative x with respect to s is t squared. Wow, it's t squared. So I put t squared here. Well, it doesn't matter, it's time. Plus partial derivative z with respect to y, que es e to the x t squared again, cosine x squared t, multiplication by the partial the y with respect to s, que es 2st. 2st. Everyone follow me? I want to copy directly to save time. The second using the same technique, no? Is 2st e to the st squared sine x squared t plus x squared e to the st squared cosine x squared t. Does everyone follow me? You understand very well. This is easy. This is no big deal. This is straightforward. In my opinion, the most complicated part is the derivative formula. But actually, it's not complicated. Okay? Okay? No problem. No problema. Guy, answer me. Okay, good. No problem. Let's move on to another. So now I want to study implicit differentiation theorem. Implicit differentiation theorem. Okay. I don't want to derive the formula. I want to explain using example. So now we are doing one project exactly like Cal 1, and we generalize to the Cal 3. Suppose implicit. What means implicit? Well, implicit is, look. Let me explain this idea, it's important. Suppose okay, we have z equal fx comma y. Now, this formula of this equation is explicit. It's explicit because the dependent variable is c in that case is isolated. However, we can manipulate in order to put in an implicit case when you have implicit. For example, you have a capital F because it's not the same mathematical expression. You put x comma y comma z comma 0. O comma 0 or comma a constant. Equal 0 or equal constant. Not necessarily always 0, but it's okay. This is a classical idea and implicit. Sometimes algebraically it's possible to manipulate this, but sometimes no. Sometimes it's very, very hard to isolate the verb. Let's suppose, what is the project that we are doing in Cal 1? Well, I don't know exactly how your teacher in Calculus 1 are doing, but suppose this. I want to find the famous dy dx in Cal 1 or y prime, either way. And you differentiate. Entonces, you differentiate with respect the y with respect to x. Entonces now you apply here a product rule. Derivative of the first function is 2x multiplication by y plus derivative of the second, que es y prime. Entonces now remember, the idea is clear. This is like a chain rule. And the Cal 1, y depending of x only. One step inside the change in Cal 1. No 2, no 3, no 4. I did that derivatives. Now derivative, this part is with respect to y, the x is with respect to x, sorry, is 6y prime, no? Because in any place you see y, is dy dx, because dx is 1, no? I call y prime. I don't know exactly your teacher in Cal 1 see explain like that using y prime or using dy dx. By the way, it's the same. Dy dx. Sorry. Dy dx. It's a Newton notation, Leibniz notation. Okay, plus derivative with respect to x is 5, and derivative constant is 0. And now you manipulate algebraically in order to isolate y prime, que es our goal, no? So you factorization, y prime, x squared plus 6y. I move everything to the left, que es negative 5, and negative 2xy. And finally, y prime, que is our goal, is minus 5 minus 2xy divided by x squared plus 6y. And this is the final answer. Cal 1, implicit differentiation theorem. What is the goal now? Generalize that formula. Cal 3. Generalize that formula. Well, suppose I want to compute in the region, of course, partial derivative. So you express it in implicit. Okay, implicit, remember, is something like that. In this case, we have two variables, no z. Well, the only thing you should do is moving 10 to the other side equal to 0. If you want to express it in that way, however, it's possible. Put a constant. In this case, the constant is 10. This is equivalent, guys, because derivative constant is 0, you know? Okay, but it's okay. I respect this idea. I copy, I move 10 to the left. Yeah, okay, I express it in implicit. Now, notice, because you compute a partial derivative f with respect to x. Let's do it. But no like a Cal 1. No, partial derivative. Is, we see 2x, and you differentiate with respect to x only, to xy, derivative of part is 0, derivative of part is 5. Cool. And partial derivative, the implicit function, the implicit equation with respect to y is x squared plus 6y. Because 2 come here, 6 decreasing 1, derivative of part 0, derivative of part 0, derivative of part 0. And you see it's no coincidence. Okay, dy dx is minus fx divided by fy. Okay, look. This guy, this expression is exactly the same. This expression, but the opposite sign. That is a reason I put a minus here, right? And the other, no, the other is identical. This and this is the same. Okay, so this is a formula. And this formula we can apply not only in two variables, so in three variables, multiple variables, exactly like one. This is like a magic. Now, this is the antique way we are doing in Cal 1. Now, we apply the implicit differentiation theorem to find that. Do you follow me? Okay, let's do one example 2. Yes, okay. What's your name, mister? Guess 982. I don't like any name. You put your actual name. Example 2. A little bit more complicated. It's 3x squared y minus y z squared minus 4xz minus 7 equals 0. Cool. In this case, it's more complicated because we have x, y, and z. You need to find partial derivative z with respect to x, partial derivative y with respect to x, partial derivative z with respect to y, for example. Okay, according to the implicit formula, is minus f and x. So partial derivative capital F. So when you express this in implicit, actually is given at the beginning in implicit form divided by f and c. Okay, it's easy to remember because it's you swap that x in the bottom, x in the top, c in the bottom, c in the top. This is minus f x divided by f y, and this is minus f y over fc. Let's do it. Let's do it fast and quickly. Minus something. Partial derivative, this expression with respect to x is 6xy minus 4c. Checking, guys. See, I'm doing well on it. So I differentiate only with respect to x, and y and c is considered constant. And in the bottom, with respect to z, okay, is minus 2 zy minus 4x. End the story. Likewise, minus. This minus, if you want, it's a fraction. You put in the top and the bottom or in the front. It doesn't matter. You know that. This is 6xy minus 4c, exactly the same because it's the same expression, the same partial derivative divided by 3x squared minus c squared. Okay, 3, we can differentiate with respect to y. Minus, in this case, 3x squared minus c squared, I did before, divided by minus 2cy minus 4x. Derivative f with respect to c. We have no c here, we have c here, it's 2, but minus, okay. Here is minus 4x, and this is 0, 0. Cool. Super elementary. Super easy. Fantastic. Magic. This implicit theorem. Implicit differentiation theorem. Okay. Any question, guy? I promise.
On the notation.
Is
the letter, the lowercase letter dy over dx, is that the same thing as the partial y over partial x?
Yeah. Okay, let me. It's important that you understand this. So the classical no. The notation que some people prefer is this fx. Well, in this case, you know the difference between capital F and low kf. This is implicit, this is explicit. Pero, okay, focusing on the notation. This is equivalent, Mr. Partial derivative f with respect to x. Okay? And this is the Newton, and this is the Leibniz notation. Right? Let me ask a question. What way you prefer? Either way, but what way you believe or you consider? You know, sometimes in the life is something is attractive, another is repelling. No, I don't like this. Okay, what do you prefer, Leibniz notation or Newton notation?
The one on the left.
The left. Okay.
Newton.
Suppose double derivative, second derivative is with respect to s, and the other notation is df dx squared. And when there's a cross derivative is x first, y second, is partial derivative, second derivative, no? With respect to x first and with respect to y. Cool. Either way, everyone understands in the world this notation. But you need to be familiar because some subject, for example, differential equation, the teacher prefer the Leibniz notation. Advantage and disadvantage. Newton is short, but omits something. So it's not precisely in the what is the independent variable you differentiate. So now, okay, forget about it. This is just notation. Okay, now let's move on to the linear approximation. Important. Linear approximation. Okay, basically is, well, let me explain linear approximation. Linear approximation in Cal 1 is, we have a function, xy. And you have point here, a, and this is the function evaluate at the point a. Entonces we are doing, for example, a linear approximation. Okay, the linear approximation L of x is close, very close at the function, and specifically in the neighborhood of the point that you want to analyze. So the formula that we studied in Cal 1 was linear approximation is equal fa plus f prime a multiplication by x minus a. Okay, linear approximation. So the linear approximation involves the specific point. Okay, the point is a comma f of a. Okay, here and here, and the slope of the tangent line is the derivative. Do you see before, right? Yes or no? You don't need to explain any details. Yes or no?
Yes.
Yes, cool, excellent. Now I want to extending this idea in Cal 3. In Cal 3, we have a little bit different situation. We have, for example, surface. We have surface. Let me try to do my best. I'm not good in the drawing. Surface. And one specific point, let's say the peak, I want to make a linear approximation. But the linear approximation, and this is a tangent plane. No, it's a tangent plane. Tangent plane. Okay, let me try to see. Suppose one view. Suppose that we have. See, I see a lateral view in 2 dimensions. Well, so we have maybe this axis is y, this axis is x, Z, sorry, this is my view of the surface. In the specific point here, I have linear approximation. Pero the linear approximation is a plane. Everyone follow me? It's a plane, right? It's a plane. But the formula to find the plane is the same formula and the same idea that we studied before. So to get the plane, we need the point. I need to find the linear approximation in the specific point. So suppose, that's all we suppose. Que the surface, the formula is z equal fx comma y, ¿no? Entonces, in order to find the point, bueno, you evaluate f and a comma y, a comma b, que es the specific point, x and y. And the linear approximation, I want to put directly the formula. However, I promise that in one moment, maybe today, we study a super efficiency way to find the tangent plane in another way, more sophisticated, more not sophisticated, sino efficiency way. But okay, using the same analogy, you look calculus 1, calculus 3. Linear approximation, linear approximation, linear approximation. Okay, let me increase a little bit. Let me see if it's better. Yeah. Linear approximation is equal. The function, evaluate at the point, plus partial derivative with respect to x, evaluate at the point, x minus a, plus partial derivative y, evaluate at the point, a comma b, of course, y minus b. It's a formula. Look, compare. It's similar. This is one dimension, this is two dimension, because the domain is two dimension, right? And the problem is 3D. And this problem is graphical is 2D, and this is graphical is 3D. Where I come from? This one, okay, I know very well geometry in 3D. Basically, the only thing I need is a point. Okay, the point is a comma b, comma f and a comma b, so x, y, and z, and the normal plane. A normal plane is a plane here. It's a normal vector. Sorry, normal vector is a vector que is completely perpendicular to the plane, no? And with this information, we using the famous formula normal vector dot product r minus r null equals 0. It's the same I want to prove, but so far you accept this because this formula is analogous to this formula. Do you see or no? Yeah or no? No? Bueno, entonces let's see example. Yeah, absolutely. Let's see example, guys. Example 1 on that part. Example 1. Suppose we have function f of x comma y is equal 9 minus x squared minus y squared. I want to investigate, no. I want to find the tangent plane, que es the linear approximation, in 3 dimensions of at the point 1, 0. This is working like A and B, no? A is 1, B is 0. In 3D, the point would be 1, 0, 8. We come from this A, plug it in here. 9 minus 1 squared minus 0 squared. Okay? Now, the linear approximation using the formula is linear approximation or tangent plane, either way, it's the same idea. It's 8, okay, this guy is 8, plus, I need to find derivative. I need to find the partial derivative. Partial derivative of who? Of the original expression, no? You find partial derivative x. So you differentiate this expression with respect to x. Derivative constant is 0. Derivative is minus 2, no? X. And partial derivative y is minus 2y. It's similar because it's the same thing. But you evaluate partial derivative at the point 1, 0, this point, and partial derivative y at 1, 0. And we get, let me see, you plugging in here x equal 1 is negative 2. And you plugging in here and here, y is 0, this is 0. Ooh, it's 0. Okay, so my equation look like that. Minus 2 actually is minus, no plus. Minus 2, okay, it's this partial derivative evaluate at a specific point, x minus 1 is a value, a1, ab, plus 0, 0 is nothing, y minus 0. Okay, so now it's easy. The equation is a minus 2x plus 2, no? Es 10. 10 minus 2x. So basically, you can write, instead of the c equal something, I copy c approximation, no? Equal linear approximation, that c is equal 10 minus 2x. And this is the equation of the plane, no? Why is missing? The reason it's missing is because the partial derivative at this point is 0. But this is the idea. You get the idea? As always, to verify, as always, David, if you want to verify, I suppose I create one script of GeoGebra to illustrate this idea. Let me try. Okay. Tangent plane is this guy. I guess so. Yes, it is. Okay. I want to share the screen of the GeoGebra. There you go. Do you see? Yes. Okay. Look. Es obvio que the surface que we are working is a paraboloid, right? It's a paraboloid, this paraboloid up and down because the x squared and y squared is negative of. And the intercept is a 9. So at this point, it's a point 0,0,9. Okay. But this is not the point. The point is 1,0,8. Boom. Look at the point. This is our point. And what goal was determine linear approximation, get the tangent plane in this point. I did that analytically in the paper. Now I plot this to verification case tangent plane. Cool. Do you see? Guys, it's a fantastic way. When you are doing your homework and you are not sure if your answer is correct, you try to verification in GeoGebra, okay? Okay, you try. Okay, any question? Everyone saw that?
Professor?
Go ahead.
I don't understand. Does z equal L of x comma y?
What part you don't understand? Let's come back to the whiteboard.
Yeah.
Okay. Sure. Let me try again. What part you don't understand?
I just don't. So z equals f of x comma y, and that was what was given. So does z also equals L? Like z also equals a linear approximation?
Yeah, because in the in the neighborhood, o sea, the closest point, es obvio que the function and the linear approximation is the same. No? This is the idea of the linear approximation, no?
Oh, okay, yeah.
Yeah. Look at that. This is at the beginning. Calculus one. Suppose that we have a complicated surface. Wow, crazy. And you are doing a plane, que es super easy surface, the most easy surface, que is very, very close to the surface in one specific point. This is the idea behind linear approximation. Cool? You understand?
Yes.
Okay. So let's move on. Today is the important day, guys. Super important. Because we studied the most important concept today. Suppose to study gradient. Gradient. I want to explain in detail. Gradient is super important. I want to study formula. I want to study interpretation of the gradient. Okay, gradient by definition is a vector. And by definition is a vector. Entonces, this vector, the formula to compute this, entonces es, well, we can write like that, gradient, some book, gradient of the function f. Suppose that we have a function, no? It's obvious we have function in 2 dimensions. And this function now is expressed in explicit form, okay. And the gradient is a vector, and the vector is partial derivative f with respect to x, comma, partial derivative f with respect to y. Bang. This is definition. But the important is not definition. The important is interpretation. Another book called not like that gradients, you know, nabla. This letter you can never see before. It's called a nabla or del. Some book called nabla, some book called del. And put the arrow indicate it's a vector because the gradient is a vector. In my opinion, this is the most popular way. Entonces now, let me write to change something, and you take different notation. This is partial f with respect to x, comma, partial f with respect to y. Basically, the gradient, you take one scalar function. This is no vector, scalar function in 2 dimensions, or in 3 dimensions, and you compute the vector. Okay, this vector is in 2 dimensions. Okay, I want to explain in detail after. So far, we suppose that the domain is R2, XY, and the graph is in 3 dimensions, and the gradient is 2 dimensions. I want to explain in detail 3 dimensions, pero after. Okay. Now, I want to prove some important property for the gradient. This vector is important, indicates something important that I need to understand. I suppose that you remember very well level curve. You remember very well level curve. Level curve is when you suppose that the function is equal to constant, k, and k vary in value 1, 2, 3, 4, 5, or not necessarily whole number, the real number 2.5. Okay, and you obtain a family of the curve that somehow give me information about the 3-dimension graphic, but you convert in 2-dimension picture. Suppose this guy is K1, K2, K3. I suppose you remember very well this, right? So this is level curve, and the family of the level curve is the contour plot. Cool. Suppose now I have a point. I want to prove mathematically that the gradient is perpendicular to the level curve. Okay. Listen to me. This curve, of course, we can represent like any curve in the space using vector value function. Do you remember vector value function? R of t, I suppose, no? And the derivative of the vector value function, the velocity, r prime at t, is a vector that is always tangent in any point. This is the vector r prime. Another point is like that. Another point is like that. However, our famous gradient we study now is perpendicular. I don't know if in this direction or in this direction, but 90 degrees. I guarantee you 100%. Let me try to prove this. Let me try to prove this. So you know, okay, the level curve is the function equal constant. This is just a number, right? And you suppose that this curve we can represent like a vector value function. Vector value function, let me recall, is x of t, comma, y of t. I copy two dimension because it's a level curve. A level curve, the graph is in two dimensions. Now, I want to express f, not f comma y, you know, like a vector value function. So you express it like that. R vector value function t equal constant. That's the same. Instead of xy, I condense it, synthesis like a vector value function. If you differentiate with respect to time of t is a parameter, no time, both sides, and you differentiate here, it's obvious that this is 0. However, here, I have no idea, I am lost. It's a function that depending of x and y, and x depending of t, both. This is the chain rule. Okay, I know very well the formula. The formula say derivative f with respect to x, time derivative x with respect to time, the time of the t, plus, and doing this path, and the other path is partial the f with respect to the y, time dy dt. Notice that this is partial derivative because depending two variables, three variables, and this is no, this is ordinary derivative because depending only the one. So you organize this equation, okay, and this equation is equal to 0. Don't forget this. Cool. So you organize this equation like a dot product. Dot product of what? Well, dot product of this, you suppose df dx, comma, partial derivative f with respect to y, okay, is this and this, like a one vector, dot product dx dt, comma, dy dt. This is a, you know, it's another way to express the same idea. Instead of the algebraic expression using dot product. So, you know, by definition, dot product is multiplication, first component time, first component, second component, plus second component time, second component. And this is gradient vector identification. Wow, it's the new vector that professor defined. And this vector is the tangent vector, que is the derivative of the vector value function with respect to this. And when the two vectors are, the dot product is 0, it's because they are orthogonal. Conclusion is the first property I want to illustrate. The gradient is a vector, and the vector is always perpendicular to the level curve. Que es also perpendicular to the tangent vector in any level curve. So you apply exactly the same idea, not in the level curves, you know, in the level surface. I try to remember level surface. What is that? Level surface, guys. This is a complicated part, in my opinion. This graph is 3D 3D, and you convert using level surface in 2D. A level surface is the graph in 4D. Okay, you cannot do the graph. To get some idea how it look like, you create level surface and you convert in 3D. So entonces, this surface in 3D is level surface. And you have a family of the different surface que somehow give me information about the graph in 4 dimensions. Suppose this is K1, K2, K3, and so on, different value. It's a family of the level surface. And we can define, in this case, also the gradient. But okay, but again, the same problem that you have, for example, suppose z equal fx comma y is explicit equation. However, you can write like that: x comma y comma z equals 0, gets implicit. If you, for example, you compute the gradient, but the gradient in 3D is partial f with respect to x, comma, partial f with respect to y, partial f with respect to z. Now we can do that. We can analyze the problem in 2D or in 3D. I prefer. Let's see the example. When I do the example, you understand much better. I prefer compute the gradient like that in 3D. Because in this case, it's a fantastic way to compute, for example, a normal vector. Because similar to this proof I did that, in this case, this gradient is perpendicular to the level surface. Entonces you know that this is super fantastic way to find the tangent plane. So at the beginning, one function is given. I don't care if it's 4D or 3D or 2D. You consider this surface confront of the one figure in 4 dimensions. I don't see the graph. I don't understand the graph. So I consider like a level surface. I compute the gradient using that formula. Oh. Some people say, no. I don't understand very well this. Okay, no problem. You compute the gradient using the other formula. It's this formula. And you get the same answer. Okay, I encourage you using the 3 dimension. And directly, when you evaluate at the specific point, you get the normal plane that we need to the linear approximation. Okay, so this is a fantastic way. It's a preference. Yeah. Either way, Ernest. Either way. This is the, this is something gets not clear in the book. In the book, sometimes using 3 dimensions, you don't understand very well. And my conclusion during a lot of years teaching this class is it doesn't matter. It doesn't matter. So you need to create your own mechanism to do that. I want to do exactly the same example that we were doing before, using this idea of the gradient in 3D. Actually, we are doing gradient in well, we don't know what is the gradient, no? Okay, suppose this example, again, repetition, the example that we are doing before, but another approach. Suppose you have a function que es de paraboloide, remember que es 9 minus x squared minus y squared. At the famous point, que was 1,0, 8. Now immediately, I like that way. You compare the implicit formula, include C. Because you suppose que this is C, no? Entonces es 9 minus x squared minus y squared minus c equals 0. Okay, ready. And now compute the gradient. The gradient in 3D is partial derivative of the implicit with respect to x, partial derivative of the implicit function with respect to y, partial derivative the implicit function with respect to c. It's doing partial derivative x is minus 2x. Partial derivative y is minus 2y. Partial derivative with respect to c is negative 1. Look at that. It's negative 1. Therefore, our gradient. Bueno, evaluate the point. Evaluate the point. F, capital F, evaluate at the point 1,0,8. Es obvio que es negative 2. Exactly the same answer. F, evaluating y in the same point is 0. It's 0. Remember, we have 0 y, unfortunately. And this evaluate at the point 1,0,8 is negative 1 because this do not depending of nothing. It's a negative 1. Negative 1. Not depending on C. Okay, now I immediately go to the plane. Remember, plane is x minus x null plus b y minus y null plus c. Remember our knowledge in the chapter 1, z minus z null equals 0. Where come from this? This comes from of the vectorial equation, que es normal vector, dot product r minus r null vector equal to 0. So the component for the normal vector is ABC, and the component for the r minus r null is this, this, and this. In our problem now, our normal vector is the gradient in 3 dimensions. Entonces, A es negative 2, x minus 1, because x null or whatever. X null is, aquí hay confusion the notation, ¿no? X null is x null, y null, c null, plus b. But b is 0, professor. Y minus 0, similar to the another approach, plus c, pero c es negative 1, ¿no? C es negative 1, entonces actually no plus, es minus, minus, z minus 8 equals 0. Now the rest is piece of cake. Is minus 2x plus 2. This is 0 disappear. Minus c plus 8 equal to 0. Minus 2x minus c plus 10 equals 0. If you want, express the equation of the plane in the standard form. Remember, it's ax plus by plus cz equal d. ¿No? Bueno, let's do it. There's minus 2x and y is missing. Okay. C no, is minus c equal minus 10. Wow, too many negatives. There are no reason to have too many negatives. You multiply by negative 1 or divide by negative 1, 2x plus c equal 10. And you get exactly the same result we are doing before. Cool? Cool. Okay, so the conclusion is, let me try to explain using my idea. We study new vector, it's called gradient of the function. You get gradient for apply the formula, no? In the scalar function in 3 dimensions or in 2 dimensions. And you get a vector in 2 dimensions or in 3 dimensions. The interpretation is, si you interpretation in 2 dimensions, the gradient is a vector que es perpendicular to the level curve. Cool. In 3 dimensions, si you suppose that the problem is 3 dimensions, therefore the gradient is a vector in 3 dimensions, and is perpendicular to the level surface. So si es perpendicular to the level surface, we take advantage of this fact and to find a normal vector we need to determine the equation of the linear approximation or the tangent plane. Everything is okay? And that's it. Okay, that's it. And no, we don't finish. This is just the beginning. So this is the fundamental property for the gradient, but we continue to study gradient and another important property. Entonces we have now directional derivative. Directional derivative. Okay, directional derivative. New thing que es related, connecting by the gradient. Okay, entonces normally some teacher que explain calculus 3 explain perfectly partial derivative. And the student believe que partial derivative is the solution. It's similar to the calculus 1. No. Partial derivative with respect to x, y, or z, either way, is in one specific direction. Entonces, pero in the space, on the plane, we have infinity possibility of the direction. Now, that is the reason que es directional derivative. Let me explain in detail definition first, and the important property of this and the connection with the gradient. Look, definition. Okay, definition. I don't know why. Let's call using capital D U as a vector of the function scalar que es f, evaluate at the point a, b. A similar definition que you know is a limit when h approaches to 0 of the function, evaluating a plus h u1. I want to explain who is u1, comma b plus h u2. Divided minus f a comma b, same definition of the derivative, divided by h. The new thing is who is u1 and who is u2. Well, it's a component of that vector. You have a vector u1 comma u2. So basically, the idea is find the derivative in one totally arbitrary direction. Okay, and this direction is indicated by the unit vector u, que the components are u1 and u2. Okay, it's not enough in my opinion. Suppose the famous partial derivative with respect to x is under the supposition que u1 is 1 and u2 is 0. Therefore, you navigate under the consideration that our variable only change in the x direction. And why not? Why is it constant? Now, the partial derivative with respect to y is completely opposite. u1 is 0 and u2 is 1. Pero bueno, in any direction, no exactly in the classical x direction or in the classical y direction. No. In any direction. And what is important to find that? Well, it's important because remember the derivative interpretation, the physical interpretation for the derivative is a rate of change okay, of the one hypothetic surface, no? So you have one point and you need to find the rate of change. Okay. Entonces now, what is the formula que connecting somehow gradient and directional derivative? The formula is directional derivative, capital D, U. Another possibility of the notation of this, que is not frequently using, is the partial f with respect to u, and you indicate here vector. Okay, and you indicate here vector also, of course. Some book don't put the arrow, but obviously it's the arrow because U is the unit vector, is the dot product between the gradient, dot product, and the unit vector. Okay, another possibility is, you know, the gradient is partial f with respect to x, partial f with respect to y. Dot product and the unit vector is u1, u2, no? Comma u2. Entonces, when you perform a dot product by definition is partial derivative f with respect to x, multiplication u1, no dot product, you know, regular multiplication, plus partial derivative f with respect to y, multiplication by u2. Okay, so I prefer either way. That formula is okay. Dot product. It's a one compact way to memorize all this. It's the same. But I have more. This is an important moment. This is a moment that I'm waiting for this. Okay, look. Suppose okay, I want to find, but it's important to understand. Okay, look. Gradient is a vector. Unit vector, of course, is a vector. And the dot product between two vectors is no vector, it's a scalar. So the derivative, directional derivative, represents a number, 20, -5. What means that? Well, that means in the direction, okay, make a decision to travel. You make the direction using the unit vector. So in the direction of this unit vector, what is the rate of change of the hour function? It's 20. It's because it's increasing 20. So slope is 20. It's -5. It's decreasing. It's going down when the rate of change -5. Okay. Now, so the directional derivative is scalar. It's just a number. Okay, no problem. I understand that. I'm using another formula of the dot product we studied is magnitude the gradient multiplication by magnitude unit vector cosine theta. I suppose you remember very well this formula. Yes or no? It's a famous formula that we use to find the angle in between two vectors. Cool. However, what happened with this unit vector magnitude is 1, you know, because of the unit vector, no? So the directional derivative is equal magnitude of the gradient multiplication by cosine theta. Okay? I want to investigate now in what direction the directional derivative is maximum or minimum. This is important, no? So you have in the surface, I have a point, boom. So I want to investigate what is the steepest ascending in this mountain? Entonces, what is the, in other words, this is what is the path in which when you travel up ascending of the mountain is maximum rate of change. O minimum. Entonces super easy because this expression is maximum when the theta is 0 degree. Because I know very well que cosine is +1. Entonces the maximum, the directional derivative maximum of the function f maximum is equal the magnitude of the gradient. Conclusion. Okay, what is the steepest ascent? Well, so we have a surface, I have a point. Suppose you have surface, We have a point. I want to investigate what is the direction in which you steeped ascent. Well, the direction is the same direction of the gradient. It's in the same direction of the gradient. But the gradient is a vector gradient, and the vector indicates us in what directions you moving, following the command, the order of the gradient. Moving in this direction, professor. Okay, no problem. I obey. Mama, you are ascending faster, right? However, what is the direction que you descending faster? Ah, bueno, okay, it's steep descended. Steep descend. Es when it's mínimo, ¿no? And mínimo is when the theta is equal 180 pi. In this case is negative, no? The directional derivative in that direction is minimum is equal minus magnitude of the gradient, because cosine 180 degrees is negative 1, ¿no? Entonces the opposite direction. Opposite direction of the gradient. Entonces, what is the super fantastic conclusion? The super fantastic conclusion is we study now the directional derivative. Directional derivative is more general concept que involve the derivative in any direction. We studied so far partial derivative with respect to x, partial derivative with respect to y. This is weak because it's in only one direction. In infinity direction, entonces more complicated. But okay. Now we go one step forward. There's the formula to find the derivative in any direction. Cool. Now, I discovered something. I discovered another important property for the gradient. Gradient indicates also the maximum directional derivative. So the gradient is a vector, and the arrow of this vector indicates us the direction of this. Okay, and what the function increasing faster, and the opposite direction is descending. So you go back faster, you go in the opposite direction to the gradient. If you go over faster, you get in the same direction. I promise I have one example to illustrate very well this idea, no? Let me try to explain in different way. Let me try, because in education, it's super important. The one picture, maybe it's cool. Let me try. Try. Okay. Look at that. It's a mountain. You see the mountain? Okay, you see the mountain, no? Okay. Now, suppose que using topography, suppose que I here and one specific point. But suppose using topography study, I determine different level curve. And this level curve, I want to draw here, approximate. You help me, guy. 1, 2, 3, 4, 5, 6, 7. Suppose this. You accept. My drawing is not okay. Okay. And suppose I am here. I am here. In this point. Suppose. Because I want to investigate what the path can allow me to go fast to the peak of the hill. Well, so this is the tangent vector. This is the, let me use in blue color, the gradient. Gradient is always perpendicular. Okay, perpendicular. So this here is a gradient. Look, gradient. Perpendicular. You're moving for this. You're walking, taka, 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 for this. You get to the next, we have infinity levels first, technically, theoretical. But suppose que no. Suppose que you travel in this direction and you go to this point. Again, we have a tangent vector. And we have now here the gradient, okay, perpendicular. So basically, this guy me to travel, suppose in this direction, to the peak. Okay. Do you see a little bit or no? No, or confusing? Suppose que I go back y I want to descend, pero not necessary for the same path, it's another path. So you travel, for example, here to here to here, maybe it's like that, the gradient. Okay, now perpendicular, gradient. Okay, a gradient perpendicular, a gradient perpendicular. Okay. Okay. I want to show you more. Because it's important. Do you get the idea or no? I try to do my best, you know? No? Yeah, okay. Alvaro is here. Alvaro help me always. Okay, Alvaro, let me try to explain another way. Look, I want to use it, guys. No algebra anymore. No algebra anymore. I using the software que I illustrated the other day, no? Que es el 3D special. Que es good in some way it's good. Okay, I copy this link. I open the browser. Page, Control B. Here I try to open the. Okay, there you go. Let me share the screen. This. Okay, there you go. Do you see? Oh no. Do you see? Okay, I am using this exactly the same surface que default bring me this because it's important. This surface is funny because you have two mountain, no? And two violet. Okay, and for example, in the first quadrant, when both quantities are positive, in the fourth quadrant and the third quadrant, positive or negative, the answer is positive. However, in the second quadrant, in the fourth quadrant is negative. Okay, because opposite sign, no? Entonces negative, it's a value. Now, so you want to do, for example, the contour plot. Create contour plot. Here, surface. Here, contour plot. And this is important. Look, this is super. You select here. Show gradient at the point on surface. And you click here. Okay, you see in 3D and you see in 2D. In 2D, in my opinion, it's much better to see. Look. We are in the first quadrant. When you approach it to the peak of the hill, you see the arrow point to the peak of the hill. And this is super important. Okay, the gradient, when you go to the peak of the hill, is 0. And make it easy. For me, it's super logical. Because remember, the gradient is a vector que point to the maximum. So go to the maximum value, no? If you reach the maximum, entonces the gradient is lost, no direction. Where's the maximum? No, I haga the maximum. Entonces no necessary. Okay. That is the reason que on the maximum, the gradient is 0 vector. But okay, it's important. Look, in the first quadrant, always the arrow point to the peak of the hill, no? However, in the second quadrant, no, it's completely opposite. Okay, the ascending is go outside. Look, we are in the second quadrant, we are in the valley. Okay, so now we need to increase. In this quadrant, no. In this quadrant, point to the peak of the hill. Okay, and this, no. Completely opposite. Go away to the, because as you want to ascending, you need to go in the opposite direction. Do you see now or no? Okay, cool. Let's move now to the whiteboard. And let's do one example numerical because tomorrow blah 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 today, professor. Okay, let me try share the whiteboard. Switching to whiteboard. Here over there. Cool. Erase everything. Okay. Suppose example to illustrate directional derivative, gradient, Okay, you have function c equal f of x comma y. Okay, by the way, is multiplication of x times y. Well, it's a quadrant, pero es weird quadrant. At the point P, okay, it's the point 2, 1, 2. It makes sense, you know? See, it says x, it says y. When you multiply x and y, give me z. Gets 2. Cool. You find first, number 1, find the direction of steepest ascent at the point P, P and 2D is 2, 1. And you the question have two parts. In that direction, you can express it. Remember, you can express it direction like a unit vector or like an angle. Either way, I prefer unit vector, but it's possible. And that direction, so you travel in that direction, what is the rate of change? Yeah, this is a number. Rate of change is 40. Okay. And second question, say find the direction to go increasing, so that means positive rate of change at half divided by 2, half L. Half this rate of change. The question say, let me try to understand the question. The question says, suppose that you compute here that the rate of change is 40. I want, and this is it's obvious that it's steeply ascending is in the same direction of the gradient, no? However, I want to find in what direction the rate of change now is 20 divided by 2. No, well, I don't know. Let me try. So you can express it like an angle, or you can express it like a unit vector. Either way. Okay, easy. This problem is easy. Number 1, you can find the gradient. In this case, I prefer the gradient in 2 dimensions. So, I don't know. Gradient of f. Okay, it's partial derivative with respect to x and partial derivative with respect to y. I prefer in 3 dimension, guy, when you need to find the tangent plane. But in this case, it's better like it's given, no? In implicit. So now, partial derivative with respect to x is y. and partial derivative with respect to y is x. Wow. Now our gradient specifically in our problem is y comma x. Cool? Cool? Now our gradient in this surface specifically at the point 2, 1, okay, it's the point gets given, no? At the beginning, look, 2, 1 is the vector 1, 2. Because remember, you see y, this is x value, this is y value. So y is 1 here and x is 2. Now, if you want to find direction of this vector, wow, it's easy. You find the magnitude of this vector. Square root 1 squared plus 2 squared. This is square root 5. And you divide the vector divided by this. So the famous unit vector can indicate direction is 1 over radical 5, comma, 2 over radical 5. This is detailed, rationalized or no, professor, doesn't matter. I don't care. This is nothing for us. In my lab, get picky. They want rationalize. However, in the paper, no. So there are one difference in between when you're working online, because online is picky, or online is formal. Online say, express your answer to the near 100th. You put 3 decimal place, this is wrong. Okay? Well, in my paper, no. My paper, I accept any smart answer. Okay, so now one answer for that question is, well, is the direction is pointing for this unit vector. Okay, so you are in the point 1, 2, 2, 1 in the point, and that you move in that direction, our rate of change is maximum. Okay, and they say, well, professor, I don't like this answer. I like an angle. Okay, no problem. Eso es easy. Angle is super easy. Angle is, you find the angle of this vector. So angle theta is equal to tangent inverse of the component y, que is 2 over 1. And you put in the calculator, no? It's 63.43 degrees. So you are surface. You have a point, que the point is 2,1. So you move it from this point and using this angle, okay, suppose que es positive. So this is measured with respect to the x-axis. Okay. One idea is, this is my sketch. I want to illustrate after in GeoGebra I have. This is the famous point, SSX, this is y. The point is 2,1, 1, 2, 1. Here is my point. However, the vector is 2, 1, 2. So 2 up, 1 here. This is a vector. And this angle is 63.43. And also, this unit vector indicate direction is this guy. Cool. I want to illustrate very well in GeoGebra I have on screen. However, let me try to answer. No. Wait. Entonces, what is the rate of change? What is the rate of change? What is the rate of change? Ascending, steepest ascending. Well, no, it's the magnitude of the gradient, que es radical 5. Bang! This is the second answer. So when you are in this surface at the point 2, 1, and you go steepest ascending, you travel in the direction of the unit vector 1 over radical 5, 2 radical 5, and the rate of change of your height is radical 5. Cool. However, I want to finish the problem when in what direction I go, half. Okay, the second part is when, okay, the problem is, see the directional derivative. I need to find directional derivative in the unit vector. I have no idea. with the function in 2, 1, okay, is radical phi over 2. So you take this, get the rate of change when you travel in the direction of the gradient, divided by 2, because the problem says get divided by 2. And so now I know that this is equal, okay, this is equal the gradient, que es radical phi, cosine theta. Now I repeat again, directional derivative of the function is equal to the gradient, multiplication by cosine theta. And what is theta? Theta is the same theta of this. Let me call another letter, no theta anymore. No theta. Let me call alpha. It's another angle. Alpha. Entonces es obvio que cosine alpha es 1/2, ¿no? Look, cancel out this and this. This is 60 degrees, plus or minus. That means que our rate of change, que when you travel in this direction, is radical phi. When you travel, let me using another color, maybe blue. When you travel in this direction, or in this direction, okay, this direction is 60 degree here, or minus 60, okay, from this 60 degree. So for the direction for the gradient is 60 plus or 60 minus. O sea, es 60 plus 63.43 is 123.43 degree. This direction lie in the second quadrant. And minus 60 plus 63.43 degree is 3.43. This direction lie in the first quadrant. Okay, pero make sense, right? Okay, so we finish the 4 minutes that we have to see the GeoGebra. You know, guys, one picture is much better than 1,000 speech. As you see that, maybe you understand more clear. Okay, let me try. This is the complicated part for me. Now open GeoGebra. Open. Let me see. Maximum mirror radius, maximum tangent. Gradient. No, it's not here. Oh. No, this is directional derivative. Okay, it's the same problem. Look. Okay, I got it. Let me share the screen. Switching. Do you see? Wow, too much. I don't understand anything. Okay, look. This is my famous function in 3D. The famous function, remember, was x times y. Is the hyperboloid parabolic. But weird, rotate something. Entonces, there's no clear identification. I am doing the surface. Look, the surface. Level curve. I see in that graphic more clear the surface. At the point B, is our famous point 2, 1, I do the vector. No, this is the gradient vector. Let me. This is the gradient. The gradient is u. This is the gradient, like a flashing gradient. And this indicates direction and what that function increases faster, steepest ascending. According to the level curve, this is 1, 2, 3, 4, 5. Okay. Now, in the other direction, get 60 or negative 60. I don't know why the GeoGebra don't allow me to put the opposite direction. Is when it's a half. It's obvious, no? It's obvious. Now, this vector do indicate magnitude of the rate of change, indicate direction. In what direction the rate of change is half. Okay, it's obvious. So because we go slow when you travel in this direction, and you go faster in the direction of the gradient. Cool. Do you understand very well today or no? I know that this is complicated. Okay, little by little, no? Little by little. Remember, guys, don't you what is the way to learn this? In my opinion, the way to learn this is doing the homework. When you, for example, stop in the homework, ask for help. Do you see my face now or no? You see my face? I stopped sharing. Yes. Okay. You are doing the homework. You, as normal, you are students, you're stuck in one problem. You ask for help. Ask me, the tutor, or no. You email me with the screenshot of the question that you want to help you, or go to the, remember Jose Alegre. Jose Alegre is the tutor. It's the only tutor que very well know calculus 3. Okay, no, the tutor. You enter here, get calculus 3, no. I don't remember calculus 3. Okay? Entonces, now take advantage Jose Alegre and me. And also, you know, okay, before the test, I make a review package, a review for the test, que is somehow similar to the reading test. Okay? Okay, entonces we finish. Time is over. We gotta go. Nice day. Sound good? Yes, always. You only pay attention. Yeah, I am so proud. I feel that you are good class. You are good, excellent class. I am so proud. I am very lucky. Yeah, I am very lucky. Yeah, I have students like you. Unfortunately, the other class I have, the pre-calculus, is good, also good. Sometimes it's horrible. So, you know, you are good. Okay, bye.
Professor.
Take care.